the third lecture of Francis anyhow, so far recorded in the, improvised way. Hopefully we'll fix it.
Okay,
In the
thanks.
meantime.
There is Nati hiding behind to ask tough questions, if need be. So let me give like a brief summary of what we stopped at yesterday. Because the goal is to take the minimum of some function h, okay, and this was in a set omega, and we formulated it as a supremum of finally the largest lower bound, and this was this, that h of x is equal to c, and we use a sum of square relaxation, h of x. Okay, so we started with this. So I think what we have. So this is a classical sum of squares relaxation where I replace positivity at that function by being a sum of squares, based on like some future vector phi. And what we did yesterday is to take now phi infinite dimensional, and phi was now from omega to f, and f was a feature space, a feature map associated with a kernel k. Kernel k, and k was essentially a Sobolev space. Okay. And so this had so what I showed yesterday is that although typically there is a gap it's only like greater here if you take like such a setup, and if you make some assumptions on h, like it's symmetrically differentiable and around the minimizer things are well behaved, then there is tightness, so there is some A star here that will achieve the global optimum. So this is a consequence of using like continuous functions or differentiable functions and not polynomials. Okay, there's no more algebra anymore, it's just a matter of regularity, and this is helpful here. Then we realize that here we still have to consider this, which is for all x in omega, and we replace this by the supremum, still C in R, L, PSD, but now we're going to regularize L because we're going to replace this like continuous set of equalities by simply for all I in 1 to n, same thing, h of xi equals to c plus phi of xi transpose phi of xi. So this has a nice consequence of only accessing h through function values. Okay, so this was the whole goal. One of the goals that we had with Alessandro Rudi and Ulysse Marteau-Ferret. Then, so we access h through functional values, only n of them, okay, and the hope is that with a proper regularization, things work out fine. So what we showed, well, what I alluded to yesterday, is that if lambda well chosen, then the number of samples needed to get precision epsilon was of the order proportional to epsilon the minus d over m minus 3, where m is the number of derivatives that you have on the function h. Okay? So let me pick out the strong limitations that results first. Okay, so first, lambda has to be well chosen. Okay, so in our scale it's not too bad because as opposed to like machine learning or supervised learning, we can, once we get a potential minimizer x, a candidate minimizer x, we can simply like choose lambda with the minimal possible h. Okay, so there is a cross validation here. It's not too difficult. So first limitation. Second limitation, there is a constant there, which depends on h. Okay, in ways which we don't totally control. And even worse, that depends on d in potentially exponential dependence. Okay, so this is a strong dependence, and and the focus here is to focus on the precision parameter, on the exponent in the precision parameter. Also what I mentioned yesterday, that the optimal way of optimizing a function with no only knowledge of function values is epsilon the minus d over m. So this is a lower bound, it's a minimax lower bound. You cannot do better in the worst case. Okay, so this was what I ended up. So this is still nice, but we still have to optimize this in one other point, important. So if lambda is 0, okay, so if lambda is 0, I'm not going to do the math, so you can check that essentially you're going to take that C star will be the minimum over I of h of xi. Okay? So what is this algorithm? It's simply a random search. Okay, I sample many xi's at random, I compute h of xi, and I select the minimum one. Okay, so this is like a reasonable algorithm, and in fact, what this one achieves is n equals epsilon minus power d. Okay, so so if you do a random search, you're not going to leverage smoothness. You're going to pay away the price of epsilon to the power minus d. And if you start to regularize a bit, then you can benefit from smoothness. Right, and then what I did up yesterday, let me finish this. I did, or maybe before I do the other theorem, are there any questions on those aspects before I move on? Yeah.
Is it obvious that the regularization should take the form trace A, or?
Oh no. So here, what we needed for what follows is any spectral norm. In our case, because our S star that we built yesterday was finite rank, like D plus 1 rank, and with every functions, every eigenvector was bounded. You can have any spectral function, sum of squares of eigenvalues, sum of eigenvalues. We took the trace because we hope that extra sparsity will buy us something, but no. Okay, it helps a bit with algorithm because it's a bit easier. But that's anything spectral will work.
So you do run this algorithm in practice, and you care about it.
I will come to defining in practice would be like different. But we can run it. We have simulations. Yes. Cool.
Can I just ask very quickly? So here you have point observations of H. That's the kind of thing you try to leverage.
Yeah.
Do you get anything, or is it just equivalent if you just took like positive linear functionals of H, or something where this is an example of like some linear function applied to H, but you could have more general linear measurements?
Oh, so yeah. So here, I think I'm not going to talk about it today, but oracles on H can be very diverse. Okay, so it can be functional values, which is common, but we have later work with Blake Woodworth when we have we observe Fourier transforms of H, which is one example of what you described. So in fact, for any way of accessing your function, you can get a different algorithm, and also depend on the setup. Okay, so if you do black box optimization, H, you only know H. When we did polynomials yesterday, we were in fact accessing the Fourier coefficients of H directly. Okay, so it depends on the setup, but this can be used as well.
Okay, thanks.
Francis?
Yeah.
Just something from back here. You need also, so what, you're not talking about what distribution you sample the x's. So you need some coverage of omega somehow. Is that coming into that prefect?
Yeah. So okay. So good question. So here, I need the xi's to be random on omega. So uniformly at random. So you have coverage. Omega is compact, so you're going to cover. And I have to admit, there are some logarithmic terms over there hidden. Okay. I didn't put the logarithmic terms because anyway we're already exponential in D, so we're not it's okay with the extra logarithm. Okay. You can also take a grid if you want. Okay, that's you can take a grid, a uniform grid if you can. Okay. So let's move on to how can we solve this in practice. And so what we have is a very similar situation as what we had for classical operator theorem, where we access the quadratic form only at function values xi, and we penalize our spectral norm. And what we had shown earlier with the same team, like Rodi, Marco Ferrer, and myself, was that A can be written as a sum over ij from 1 to n of phi of xi. So you're supported on the data. Okay, so now you have a matrix, let's call it B. other than C. Bij. Okay, now B is n by n, and B is PSD. Okay, so you can check that if B is PSD, A is PSD, okay, and you can look only for L like that. So the proof is a bit more involved than Pythagoras theorem, but pretty much almost the same. So you can look at the paper by Ulysse and me to get the thing. But what counts here is the fact that you can rewrite everything. So you can write phi of xi transpose A phi of xi. So you can look at that, you explain A, and what you will get is sum over k, S over k, sum over L j of k of xi xl b l j k of xj xi. Or in other words, k b k I. Okay, when k is a common matrix. Okay, I'm just in algebra here. And similarly, the trace of A, trust me, the trace of that thing will be essentially the trace of A will essentially be trace. It's missing something. Yeah, I think it's a trace of BK.
But that should be BKII because trace is a scalar.
What?
What do you mean by trace II? Like that would.
It's not trace, it's just the II coefficient of KBK. So K is a n by n, B is n by n, K is n by n, so everything is n by n. And alright, so now this means that that problem, okay, essentially you get here, you get h of xi being k, bk, ii, and b, now you replace it by b psd. So you have an n by n matrix, you have like linear, it's the SDP, okay, linear objective, linear constraints. So you can use any of your favorite algorithm to solve that, either entire point method, or we have like a dedicated Newton algorithm for that. So one of the nice benefits on top of classical sum of squares that the problem, and let me write the problem here, is simple in the sense that coding it from scratch is possible. I did it, okay, so it means possible, okay? So the problem at the end is the sup of C minus lambda trace of A, so that h of xi is equal to C plus k bk ii, and this is trace of bk. Okay, and so as opposed to classical sum of squares where you have hierarchies and just like writing the problem takes you half a page, here it's still in high dimensions because of course here this is B is PSD, but B is n by n, so it's quite big, but at least this is still like polynomial, and this is for all I. There's one advantage is that you can simply use subsampling, and in fact, so we are not the first ones to look at that type of problems. Even for polynomials, you can do so. So Pablo Parillo and colleagues, they have a way of doing subsampling as well, which we do similar things. But so this is polynomial time. Any questions? So one thing is that you can, this is a context problem, you can do add Lagrange multipliers, okay, and the Lagrange multiplier alpha I here will allow you to build the candidate X. Okay, so here I just have presented guarantees on the value of the optimization problem. You can get also guarantees on the optimizer, and if you want to know more, you can look at the paper. Okay, so this is a possibility, And so in the paper as well, and I won't show figures, but we apply that in dimensions which are not great, not big, but like 10 to 20, and it works like, because simply you need to invert matrices of size n by n. So you can, depending on the size of your machine, you can go to n being 10,000 or more. Okay, this is just like, you get a sequence of matrix inversion to solve that.
Is there any constraint on the matrix K?
So K here, so K is a kernel matrix, okay, the matrix of pairwise evaluations. So K will be PSD, and in fact it is crucial that it is invertible. Okay, so this means that you really need to use a true infinite dimensional kernel for which the kernel matrix is invertible. If you use a Gaussian kernel, the spectrum decays so quickly that it will be numerically of low rank, and this will not be working. This is why we use the exponential kernel. So what we use is k of xy is exponential minus x minus y2, and there is no square there. Okay, so that for that kernel on the uniform on the cube, the decay of the values is 1 over m to the power d. Okay, whereas for the Gaussian kernel is exponential. Okay, so you really, in fact, it's not very well known, but the Gaussian kernel in practice is not infinite dimensional. Okay, it's up to your massive precision, and typically it's like dimension. The small dimension can be 1 or 40 or 50. It goes very quick.
Okay, thanks.
No more questions? Yeah.
Yeah, can I just ask, so you said that, choosing the particular spectral regularizer you had, the trace of A, you could have replaced it by other things.
Yeah.
So looking at the final formulation of the problem that you have,
Yeah.
do you view it as good or bad that, in the thing you're maximizing, it's homogeneous of degree 1 in K, and then your constraints, it's homogeneous of degree 2 in K?
K is fixed, so K is fixed, and you have to remember as well that often the diagonal of K is 1. Okay, so K has no dimension. Okay, so
I see. So you don't want KBK to appear in the regularization. You wouldn't view that as more natural.
I think no, you're correct. If I think the good value of lambda will be homogeneous, it will depend on K, such that if you multiply K by 2, the lambda that you propose is divided by 2, multiplied by 2 as well.
Oh, okay. So that's gonna. Okay, I understand.
So now let's move beyond optimization. Oh, and before, let me. So let me just like redo a bit of duality just for the because we're going to extend this to more problems. Okay, and we will see that this sum of squares can be done in the primal or the dual, and let's see what is the difference. So what we had was mean over C such that C h of x minus C was positive, and this was the dual this was max. And this is mean of the integral of mu of x h of x dx, so that mu is positive and integral of mu of x dx is equal to 1. Okay, so this was primal dual formulation, which was the direct representations of minimization of h, and the two of them have a similar structure. They have some inequalities which are satisfied for all x. So this is for all x, and this is mu of x for all x. Okay, so you may want to choose to do the SOS relaxation either there, saying this, I'm going to replace it by the sum of squares, or I'm going to replace this by the sum of squares. Okay? In fact, when we started to work on that, it was not formulated this way, but we started by trying to do a sum of squares there. Okay, so we say, oh, mu is positive, let's present it as a square of a function and do a sum of squares here. Here it won't work because at the optimum you expect mu to be a Dirac. Okay, so mu will be converted, which is very, very non-smooth. Whereas here we expect that the the sum of the positive function will be close to will be well behaved. So whenever you have a set of primal dual problem, you should try to do the SOS relaxation on the side where you believe that the non-negative function will be like reasonably well behaved. Okay, so here it's clear in retrospect that this was there, but it took us a while. Okay, so in all problems that I'm going to describe now, there's always a choice between primal or dual. Okay, and you have to choose wisely between the two. Alright, so let's see what we can do more generally. So I will first give like a very generic formulation and then specialize to optimal control. Alright, so let's assume you have a generic problem. Which is you want to minimize f of theta such that for all x in your set, g theta of x is positive. Okay, so it's a very generic problem. You need, for us, f convex. Theta can be anything. Well, anything, vector space, okay? It can be like infinite-dimensional vector space. And here we need linearity in theta, in the parameter. Okay, so if you have something like that, you can always say, oh, one relaxation is simply to replace this by a sort of square. So this always works. You can always try to do that. And if you expect at optimum, for the optimal theta star, if you expect g of theta star in x to be well behaved and smooth in x, then this will give you an algorithm and probably some guarantees as well. Okay, so this is very generic, and this works all the time. You have to be careful that there's also a dual to this, and very similarly to this, there is a better place to do this SOS relaxation, primal or dual. And I will show an example in a moment. Okay, so we have two that we have worked out totally. Optimal transport, which I will not cover today. And this was by Bach, Viala, Rudi, Muzelek. So this is like the monster, okay, and myself. And this was last year, I guess. Yeah.
So Francis, is there one way to think about it would be the following, that you're trying to say solve this search problem,
yeah.
And in the theta space, you are searching for a needle in a haystack, something that is exponentially small, but in the x space for the right theta star, you're saying it's actually a smooth function, so it's so therefore you put an SOS there, and that's how you can find it. So,
in fact, there will be like so about the optimal transport, but this is I will do it for the optimal control. You see why this is happening. Right? So we did that for optimal transport, and I cover similar thing that if we have like smooth densities, we can compute the translational distance with like a good complexity. But let me do optimal control. But I think it's more fun. And okay, so let's do optimal control. Optimal control, and essentially reinforcement learning would be exactly the same thing. Okay, so and this was done with Héloïse Berthier. Okay, no relationship with Raphaël Berthier, Carpentier, and Rudi again, and myself, and this is this year. And so what is optimal control? So the idea is that you have some dynamical system, x dot is f of x and u at time, okay? So you have so this is your state, this is your control. If you prefer RL, this is S, this is A, okay? And the goal is to minimize the integral from 0 to t of some loss L x u. If you prefer, this is R of SA. If you prefer, and you maximize, if you prefer like RL, and plus you have some terminal cost. Okay, so this is a generic optimal control problem, and of course it's mean with respect to U. Okay, and U is a function of time. Okay, and you want that, you want to control your rocket to go to Mars. Okay, and you want to minimize some costs along the way, plus you want to reach destination, hopefully. Okay.
Does mu depend on the state?
There's no mu.
Mu.
U. Oh, U. Yeah. You, at the end, you want to learn a function of U. Okay. It turns out that the optimal control will depend on X typically. Okay. It will be let's go like feedback control. But I don't want to go too much into the details. But like in RL, often you end up with not having a control defined for any time. You get a function, give me a state and a time, I will give you the control. Alright, so it doesn't seem super obvious that this is entering that framework, but after like a few years of like research, you have the so-called like Hamilton-Jacobi Bellman equation. Okay, all the name given by Mike yesterday, which is maybe not Bellman, but soon you probably mention it, which is that if you call that the value function, so this is the value, so if you start, typically you start at x0 at some x, okay, so this is the value at 0 at a given x, okay, and so you can define a PDE that will solve the problem, and the PDE, maybe not able to do it by heart, but it's dv over dt plus L of x tu plus probably f of x tu transpose gradient of v equal to 0.
You define the V as...
So v, let me just make sure. So I defined that so I have an initial problem.
That has to depend on t, right? The left hand side.
So here this is the value function at 0. Okay. So you define, you have a problem which is defined. I start from 0. Okay. And I'm going to call the optimal value. It will depend on the starting point. Okay. Yes. And I call that v of times 0 and x. So it depends on x, the optimal value.
Is t fixed? Like big
There's capital T is fixed. Okay, so I define, if you prefer, I can define this as v0 of x. Okay, so I define the function of x as the minimal value over all controls of the system started at time x. So this is this function of x. And now what is a result of like whole books dedicated to it is that if you solve that PDE with Vt equal to m, the terminal cost, if you solve that PDE, the value at time 0 is what you want, and you can recover controls from it. There's a mistake, there should be an int somewhere.
What is M? Oh.
No, it's bigger than so.
Wait, what is this?
Yeah.
M is the term.
And L is the final cost. So if you want in RL, typically in RL, this is not with a finite horizon. You have like a discount factor, and you play the game. You run the thing forever. This is essentially the linear programming formulation of the optimality for the Markov decision process. So I'm more used to the optimal control, but it's essentially RL, okay? And so optimal control can be solved by having a big PDE. So here, of course, I assume I know the loss, I know F, very much like Jan was presenting. This is that do the model and you want to solve it. Okay, so this is the HJB equation to solve it. And here it's an inequation because for the expert this is just a sub-solution of the problem. Okay, so here I don't expect you to understand what this is. It's just there is a big PDE, okay, that you need to solve, and it ends up being something of that kind where it has to be positive for all txu. Okay. And so what people have done in the past, in particular Henrion, Lasserre, and Trella, so the people like in France, both with from control and from the SOS polynomial thing, simply apply the recipe, replace positive or non-negative by a sum of squares, and bam, you do SOS, and you run the machinery, and then you get an algorithm to solve the problem. In their case, if you want to apply the sum of squares, if you want feasibility, you better have that the loss and the function and the dynamics are polynomials. Okay? So this is like a requirement for sum of squares polynomials. And what we did with Eloise and our colleagues is simply to replace polynomials by sum of squares, and that's it. Okay, and what?
By kernels.
By kernels, yeah. And so so you can look at the paper. So we don't have theory at the moment because it's a bit more involved than what we had. But our hope is that if you can show that both like the V and the residual is smooth, which can be essentially ensured if you add some noise, then you have a sum of square which is smooth. So we hope that we can get some guarantees. It is not the case at the moment. Okay, it's just to highlight the fact that any infinite dimensional optimization problem you can play the same trick. Okay, and it gives you an algorithm. Any questions? So this is RL, okay? So if you prefer, linear programming formulation of RL is exactly the same thing, but with different notations. Yeah?
But it's not RL. It's optimal control, right? I mean, there's
Sure.
a major difference between those two.
I know, but I want to talk to, among adults, I agree, but for the children you want to simplify a bit, but solving MDP with known dynamics is the discrete version of optimal control.
Well, no. I mean, here you know the dynamics.
Yeah.
You know the cost function.
Yeah.
Everything is differentiable. It's even convex, linear, quadratic. I mean, it's how.
No, there's no assumptions on V and L here, but
Right, correct. You're not running it. You're just like finding the optimal control.
I agree, but I think it's RL in the tabular setup when you know everything, which is half the paper doing RL at the theoretical side are assuming this.
And also, the main thing that RL deals with is uncertainty in the model and everything, and here it's all deterministic. So.
I agree, but once you know the dynamics, this is, yeah, so here I could replace this by an SDE instead of ODE to get, but I agree with you in the fact that this is like the deterministic version of RL. You remove all the things which make RL a bit different, you get this. Yeah. But I just want to highlight the fact that in most RL books, you get that equation appearing.
Yeah.
In one form. Okay, so this is just to highlight, and you can look at the paper if you want, but I want to spend the last hour on the log sum x stuff. So let's take log sum x. So this is like the so log sum x and entropy. Okay, and so this is like myself alone in my mountain house in Jura playing with entropy. Alright, so the idea is what? So the idea is that we want to replace, what we did is, so first I go from min to max because it's easier, it's more adapted here. Okay, so I'm going to, so what we try to do for the last 4 hours is to maximize functions. Okay, we'll minimize it, but I think it's the same. And now what I want to look at is more, so the log partition function. So I'm going to control epsilon log of the integral of exponential of h of x over epsilon dqx. Okay, so it will be like some base measure think of it as uniform, Lebesgue, whatever, simple. Epsilon will be, okay, to be a temperature. Okay. And so there are many reasons why you want to study that object and approximate it. Okay, I think this is well known in physics. From the optimization side, it's often a way to smooth the maximum. Okay, so the maximum typically is not a smooth function. So if you have some parameters inside, if this maximum is not smooth in H, this one is smooth in H, so this is typically interesting. And often you want smoothness because it's easier later on, or even for optimization. So often you add this log sum x for optimization. This is for the, if you want to just use this as a tool, but it's also used a lot if you want to do probabilistic inference. Okay, so probably like in the previous summer schools in physics and machine learning, there would have been like Martin Wainwright and Mike Jordan explaining how this is an object that you need to do probabilistic inference. Okay, so there's a nice book by Martin and Mike that I really advise you to read. Okay, and so this is important. Let's assume that. How can we compute it and deal with it?
Francis, can I ask you just
Yeah.
Okay. Why change the sign of the energy? Like, I mean, I understand that it's easier and it doesn't matter, but like for people from statistical mechanics, you'd really want to do the mean of H and put a minus in this exponential. So
In fact, as I was saying, let's go to the max. I had forgotten y. Okay, so you're pushing y. Oh no, for contextuality purposes. I don't have to get minus.
I know, but it kind of made a connection with statistical mechanics a little bit.
Okay. Point well taken. And so my whole paper is written with H like that, so it's going to be. But there is one reason which I forgot. Is yeah, I don't like taking minus everywhere, but that's okay. But point well taken, and hopefully you can translate on the fly. And so the way we're going to formulate this, okay, is a very traditional way. So that quantity is simply the supremum over all distributions. So P probability distribution of the integral over h of x dp of x, okay, minus epsilon times the relative entropy interval of the log of dp of x over dqx times dpx. So this is a classical result from convex duality. So this is actually convex duality between like maximum likelihood and max entropy from my point of view. But this is like essentially classical. So the way, if you want just to prove that, okay, just take this problem, take a derivative with respect to p. Okay, you obtain that p is essentially proportional to that. Okay, and you get the result. Do you want me to do it, or this is like something that you agree with? You agree with this?
Except for all the signs, but.
Well, you can think of this H the way you draw it as if there is a small minus like that. That's squiggly, like the minus.
Yeah, okay. But so essentially, this is a duality which I've been doing like I've been doing a lot. Okay, so if epsilon goes to 0, you recover that this is a max. And this is a sup of an integral of a measure. Okay, so essentially. Alright. So now the question is, I'm going to give this a name. So this is a relative entropy. And so here, what is nice is that you see a term appearing, which we have dealt with quite often since the beginning of the lectures. Okay, the integral of a function h. Okay, and in particular, if h is represented as Q of x transpose h Q of x, I see appearing my moment matrices. Okay, so what would be nice is that can I represent this, and we call that dpq. Is there a possibility to lower bound upper bound dpq only based on the knowledge of moments of phi of x. So that will be the goal. So the goal is approximate, so in quotes, because I did making this more precise, approximate dpq from only moments, so sigma p, which is the integral of phi of x transpose, dpx, and sigma q being the same thing. Why is it nice? Because if I have a function that depends only on sigma p, sigma q, and the other part depends only on sigma p, I get a nice convex differential problem on a set of moment matrices, which I know how to relax because of sum of squares, and I will be able to compute that, approximate this, and get like do things that I like with this log sum x. So this is the goal, and let me describe the first failed attempt. And this is Bach and Mike Jordan from 2002. One of my first papers. Okay, so it was not the whole goal of the paper, and it's not a big failure, but that part I was not happy with. And one way that you can think of is that those are Commons matrices. Okay, so let's imagine that I have Gaussians with those Commons matrices and build a KL of the Gaussian KL for those. Okay, so the Gaussian KL will be up to sine log det of sigma p sigma q minus 1 plus 1/2 of trace of sigma p minus 1 minus dimension over 2, and there's maybe a minus sign. No, it has to be plus or minus. Let me check. Minus, but I don't see where the minus comes from. Yes, it has to be convex in P, so there's a minus. Alright, and so this has nice properties in the sense that it's 0 if only sigma p is equal to sigma q. There's a link potentially with the information theory, which we try to make with Mike, but it's a bit contrived. But you don't preserve many of the nice properties of d of pq. Okay, so that relative entropy is very nice. It's jointly convex in P and Q. Okay, there are many things that are not preserved. If you go to infinite dimensions, there will be a problem here because of dimension and others. Okay, and there's no directly with scale.
Sorry, this is the lower bound you get for dpq?
No, this is the first attempt to relate information theory with moments. And people have done that, defining like divergences based on moments, not a new idea. But if you take the first one that comes to mind, which we did like 20 years ago, you don't get something interesting. Okay, so now let's do something interesting.
Francis, if I think of just Q as the say standard Gaussian, would I lose a lot, or is it?
Oh, you lose a lot because you would lose a lot because so here. So what we will have now is that we will derive bounds which are true for all P and Q. So if you take P and Q Gaussians, essentially you have a very particular case.
No, so just Q is a Gaussian.
Just
the baseline Q is like the standard
you
Gaussian.
could. No, we cannot because you need to be on the compact, but you can take Q simple, it will not help you. I don't know how it will help you. So let's look what we can do. So let me give dpq here.